Okay, when this structure deforms, the structure will deform this way. This is how the structure will deform. Okay. And at point C, at the top of point C, I'm going to call it point alpha. At the bottom of point C, I'm going to call it point beta. Okay. So I'm going to sketch another line. Okay. And this line is known as our centroid. Okay. And we know that the centroid is determined based on geometry. So if you see how the deformation pattern is working on, but before I go on, what I'm trying to explain, what are we trying to drive at is why and how to apply where stress X is equal to minus mz over izz multiplied by y. Why we have to have a minus down here? Okay, that's why I'm doing this for. Okay, so this is how the structure has been bent. That's the deformation pattern. And we know that at a certain point over here, this is known as the center of curvature. And when from the centroid, okay, from the centroid, if the geometry is going towards the center of the curvature, y is positive. Okay. When the distance is going away from the centroid, away from the center of curvature, y is negative. Okay. Now, based on the observation from the deformation at the top, it's going to be what? At the top is going to be going through what? Anyone? Is going through compression. Because the circumference on that surface is smaller than the one furthest away from the the one furthest away from the center of curvature. And over here, it's going to go through what? Tensor. Okay. So when we apply the formula, okay, when we apply the formula, when we want to find alpha, right? We want to find alpha, right? We want to find alpha. For alpha, y is equal to what? Positive. Yes, for alpha, y is going to be positive, right? So when y is equal to positive, when you apply the formula, stress X is equal to minus mz multiplied by positive y divided by izz, right? This is equal to minus mz multiplied by y over izz. And it's correct because at point alpha, it's going to go through what? Compression. Okay. Now we look at point beta. At point beta, y is equal to what? Negative. So stress X is equal to minus mz over izz multiplied by negative y. Negative and negative becomes what? Positive. Okay. So that is why at beta, our stress is tensor. Okay. Now, I'm going to teach you an easier way to know whether is it tensor or compression, or if you forget there's a minus sign. Because this one, you have to remember pointing towards the center of curvature is positive, pointing away is negative. Another way to remember is this, okay, the easier way. We know to induce bending in that direction, our moment at both ends, so this is our moment vectors, okay, at both ends, okay, the moment vectors will act in this direction. The rule that I've created is the head of the moment vector, right, is going to go to what? Compression. The tail end of the moment vector will always generate what? Tensor. Likewise, the head end of the moment vector is going to be compression. The tail end will always be what? Tensor. Okay. I think this is an easier way rather than, you have to remember stress X is equal to minus mz over iz. Sometimes you forget there's a minus in front. Okay, so just look at the moment vector. Let me go to another example, another very straightforward example, right? So what if now, okay, what if now we have this now? What if now our deformation pattern, okay, what if now our deformation pattern look this way now? Right? And then I'm going to put this is my right, and then we have our, again, this is our point C, right, and then this is our point alpha, this is our point beta. So if I were to draw our moment vector, my moment vector will look like this. Okay, this is moment about Z, and then this is what? Moment about Z. So the head of the moment vector will be under what? Compression. And then the tail end of the moment vector will be under what? Tensor. Okay, so we know based on moment vectors, okay, where we know that stress X at point alpha is equal to positive mz over izz multiplied by y, and stress X at point beta is equal, so beta is on the compressive side, so minus mz over izz multiplied by y. You no need to worry where the center of curvature is. Why I devise this method is because later on we have bending not caused by not about one axis but two axes. It can be really confusing. If we are going to apply the conventional old method, we know that we have to remember that this is the center of curvature, and then we have to learn, oh, pointing in y is positive, pointing out y is negative, right? Too many things to remember. And then when you want to apply the formula, is stress X is equal, is there a minus sign? I can't remember now. Okay, then you check the book. Oh yeah, there's a minus sign. So mz over izz multiplied by y. So at point alpha, you know that what? At point alpha, y is negative. So when you put into the equation stress X at point alpha, this will be equal to what? This will be equal to minus mz over izz multiplied by minus y, and then you get positive mz y over izz. And then now you go back to beta. At beta, y is positive, right? At beta from the centroid, y is positive. Then you can say that stress z, stress x beta is equal to minus mz over izz multiplied by positive y. So this is equal to mz over izz multiplied by y, and then there is a minus sign over here. So there's a lot of steps that you have to what? Remember. Why not just apply this technique, okay, that I've just taught you? That based on the moment vector, okay, based on the moment vector that you can see over here, right? The head of the moment vector, okay, what do I mean by head? This is the head, okay? This is the head of the moment vector, is always in compression. This is the tail end, will always be what? Tensile. Okay. Right. I'm going to stop over here. I'm going to post the homework tomorrow. The homework will be based on eccentric buckling only. Okay. If that's the case, thank you for your time. Thank you for your attention. I'll see you all next week. I'll still be around.